R12, right? Which is an increasing function of R12. So if I were to plot F versus R12, it will be more like this. Farther away they are, more the probability of their being farther away. And then this gets multiplied by the other function, and then sometimes the wave function will be like this. So if you like, initially, just the product would have been phi 1s and phi 1 and phi 2. I add the interaction. You add the interaction and you go one particle like this, the other one would be like this. They go far apart. The distance between them increases. How should this R12 dependence be? Right, and this is, I've given you one problem in the assignment yesterday, and now you see the Coulombic problem has this singularity at Ri equals Rj, and if you want to avoid this singularity, one factor Frij, you should have a factor with R12, let me write this as R12, with 1/2 in front. And then something here, which we can write as B R12, 1 plus. What is important is this factor, half. If you take this kind of factor, avoids the singularity, cancels the singularity in the wave function, in the Hamiltonian. Then whatever you have, it is a regular function. So, for example, I could write the two-particle wave function, R1, R2, as equal to phi R1, R2 only times this factor, 1 plus half R12 is equal to minus B. I'm designing a wave function, alright? And I determine B by variational procedure. I calculate the expectation value of the Hamiltonian and minimize it with respect to B. If I want a multiparticle wave function, psi R1, R2 and so on, I could write this as phi R1, R2, the product wave function, okay, multiplied by 1 plus 1/2 Rij e raised to minus beta r. And there is something which is known as the Jastrow factor. This is a factor that takes care of electron-electron interaction, keeping them away. The wave function becomes, the probability of their being far away becomes greater, and then comes down. Is that okay? So we looked at an exact property called, I'll call this the R2 plus condition. For lack of a better word, although this is given more in terms of the density at the nucleus for atoms, but here also the singularity is the same, so we just call it R2 plus condition. Okay? And there's a problem in assignment given related to this. Is that okay? So we make this wave function and design the wave function and do this. Now this kind of factor is taken and this problem is done in quantum Monte Carlo. Alright, so these are quantum Monte Carlo. But you're designing, you're using your brain. You're not just solving. Alright? Now, so that's one thing I wanted to introduce. Any questions on this? Is the idea clear? The motivation clear why we are doing this? This is to keep electrons apart.
Sir, why are F decreases at large distance?
Why what?
F decreases at large distance.
F is not decreasing. F I am saying, F, because electrons cannot be infinitely far apart. Finally they are bound. Right? So they need not be just nearby, they'll go a little farther apart, then the probability goes down. Right? Anything else?
So, what exactly is the condition? I mean, is it just
That cusp condition. It comes because in the del square operator you get a term 2 by r this thing, and you want to cancel the singularity of the Coulomb part. So your wave function is designed in such a way that in the Laplacian you get a term which is 2 over r d phi by dr or d psi by dr, that cancels with this exactly. In fact, if you do the hydrogen ground state problem, that precisely gives you the answer.
So the form of a R12 is the limit.
The condition is at R12, half R12. That the condition actually, if you look at the atoms, it is that 1 over psi, d psi by dr, r tending to 0 is equal to minus z, the nucleus. Alright? That's the condition. So with that, you see that d psi by dr is psi, you do 1 over r, you get z over r, and that cancels with the Coulomb term. Okay? Okay, so that's another way. I'm going to introduce you to something else now. And this also tells you what, not just the wave function, what happens when you include electron-electron interaction. This becomes quite important. And this morning, I think Janita was asking about this. Next is, go to low density. Electron gas. Well, in the low density, right? So that means the density rho is going to 0, or the RS, the nucleoside radius, is going to infinity, where RS is defined by 1 over 4 pi RS cube is equal to rho. Okay? If you go to this limit, what you get is something called the Wigner crystal. Okay? And what it is that the electrons start, they become a BCC lattice. Okay, let me make a lattice. They start coming to form a BCC crystal. Alright? So this is again because now in that case, the kinetic energy will be 0. Abhishek, you were asking this morning. Kinetic energy will be 0 and everything is Coulomb energy. That's the stable configuration. Alright? And in this case, you can calculate the energy of the system. Alright? And how do you calculate the energy? Now that they are just sitting around there, there is this positive charge. I can take a sphere of radius Rs and put the electron in the center. That's it. That's the energy per electron. And if you calculate this, it comes out to be minus, I think, 0.456 over Rs. But this is the limit of very low density. So that's another absolutely extreme that you have for correlated problem. Now where they're sitting is a correlation, they're correlated with each other. So that's the other way. And then there are other techniques. One is known as the RPA technique. And what you do in this is that the interaction energy is related to the response function of electron gas. Now this, you can find an exact expression that makes perfect sense, because if there is an electron moving around, it's going to apply an electric field to the other electrons. And that's what causes the electron-electron interaction energy. So you can always relate it to the response function. Alright? In fact, it is related to the imaginary part of the response function. And what RPA does, so this can be written exactly in terms of, let's say 1 over epsilon q omega. Where q omega, epsilon q omega is the dielectric function. What RPA does is, if epsilon q omega is something called the Linhart response function. So that is calculated from single particle orbitals. Right? In case of solids, it's the plane waves. Okay? Then you get the RP interaction. So these are different techniques, but what I'm saying all this is different things, different techniques are applied at different places. You have the low density system, okay? And this term, by the way, was introduced, and you must read these papers. They're beautifully written paper by Hohenberg-Kohn. What they did, in fact, we're talking about density functional ideas, but they were sitting all there. What Hohenberg-Kohn did is that they took this electron gas and they said the long range interaction correlates them all, and they can do a plasma oscillation through this. And the short range interaction, then just they calculate the energy perturbatively, and they got this. Okay? The RP at the random phase comes because they took in the integration the phases of different plane waves to be random so that they could make that zero. And then this was shown, this was another very famous paper. And right, REICS, this I'm sure of. And right and Trundle. The PhysRep, these are also series of PhysRep papers. Okay? So they give you this picture, and it's a beautiful picture. So we are now thinking of these particles like this, that low regime, this is what is happening. And by the way, for densities which are not going to zero, this and high density limit is interpolated, and you get a term which is like A plus B plus Rs. This is the correlation energy, which I'll talk about in a minute. And I've given you an assignment problem. This. Fit the quantum Monte Carlo based calculation to get this form. Okay? So that is given in the assignment problem. Alright, so this is general idea of, yes?
Is epsilon the dielectric function?
Epsilon is the dielectric function. Omega is the frequency at which it is being done. So what one does, since it cannot depend on omega, it is integrated over omega, and actually you take this imaginary part, and there's some 4 pi over q square and all that. That's the Fourier transform of the Coulomb. Okay? So I just wanted to give you an idea that all this happens. Okay? Alright. Now, just why, how all this affects our everyday picture of life. I told him that without Holly's crucial principle will be kind of going into the seat. Just like that, there are other phenomena where this correlation becomes important. Now, what I'm going to define for you is, so we have correlations among electrons. One was due to Pauli principle. Right? And this was exchange correlation. And the other one is going to be due to Coulomb interaction. And this is due to electron. And both work together. And both keep electrons far apart. Okay? This is only for valence spins. This is both for this and this. Obviously they work together. So if you've taken care of this to some extent by exchange, this affects this much more. So anyway, parallel particles are keeping away. Alright? And then in quantitative thing, I'm going to define something about the correlation energy. which is going to be total energy minus E multi-Fock system. So remember I said if I write the wave function, this would be Cn psi stator determinant. And then if I take only one term, I get Hartley-Fock. Then you're improving it by including other configurations. That lowers the energy further by variation principle, and that lowering the correlation. Okay, any questions so far? Now, just to give you a physical phenomena and why this is important, and how then we can relate it to when we do DFT. This should be clear. This is important for Moore's rules. Magnetism, right?
Just a question. So, if I go from a single state element to multiple,
Yes.
so in principle I should take all of them. So
Yes.
I'm just trying to contrast the usual Hartley-Fock and perturbation series versus going beyond a single state. So
Yes.
is there a sort of map between the two that maybe going to few state determinants or that's two?
Okay. Now, variation it depends on how much accuracy you want and also your computational power.
But there is no clear map between perturbation series and
Well, I mean, but then there are some perturbation theories like Moller Classic, MP2 and all that. That one can take care of. Then you actually say that I'll go second order, whatever, before fourth order. But otherwise, in principle, there's no limit. Okay?
Sir,
Yes.
Hartley-Fock will be located at a distance of pole outside the electron. So, can't we say that correlation is still there?
Correlation will also give you. So that is also keeping other particles apart.
I'm talking about Hartley-Fock.
Yes.
We are looking at the correlation between E minus EH. That is, there is still some correlation between the parallel speeds.
Yes, so it's not just plain parallel. What I said is this is affected much more by electron interaction. So energy-wise, you will see that already you get very good energy in Hartley-Fock. It fails in a lot of other things. It fails, for example, the specific heat of solids. It blows away log T. It fails in getting the band gaps which are too high. Okay? But energy-wise, it's okay. So this is affected. This is much more. Okay? But certainly, when you do the full calculation, this also gets affected. Anything else? Okay. So this is a kind of overview, and just what happens if you do this Coulomb interaction. I'll just describe something called the Fisher wave function. I've been after it for a long time, but haven't been able to do much with it. But I think it's a very good wave function. It is, and I've given an assignment problem on this also. Okay, what it says is, you see, if I take a molecule, and this you can relate it to then again, this metal insulated transition. Suppose I take a molecule with two centers. I make two kinds of wave functions. One is known as the molecular orbital, which is, so this is center A, this is center B. I can write psi A 1 plus psi B 1. 1 is the particle, this is the this side alpha. And some normalization coefficient. Okay? This is what is known as LCAO, linear combination of atomic orbitals. I'm sure you know this, right? And the other extreme, so you do a calculation with this, so each electron is kind of in one orbital floating around, so the other one is going around, okay? The other extreme is that I write my wave function as, so the total wave function will be this times psi A R2 plus psi B R2. The other extreme is that I assume that each particle is sitting in its own center. So I'll have the wave function, what is known as the valence bond, right? It'll be psi A1, psi B2, plus the symmetric terms, psi A2, psi B. If you look at this wave function, what does this give you? This gives you psi A R1, psi A R2, psi A R1, psi B R2, plus psi B R1, psi A R2, plus psi B R1, psi B R2. Right, and this is, so this contains this. This is also R1, R2, R2, R1. Now you see there's a problem in this. There is a 1/4 chance that both electrons will be sitting right at one center, both at A, both at B, right? And that will cost energy because two electrons are very close together, right? This, on the other hand, always keeps the electrons on two centers separate, right? So this is keeping them separate. That means it is accounting for electron-electron interaction in a very severe way. It is saying always stay apart. It is underestimating the correlation. This is known as the under-correlated wave function, over-correlated wave function. They cannot be written as product wave functions. Now what Coulson and Fisher did, they showed something very nice. They said, let me write the wave function as follows. Let me write the wave function psi, Coulson Fisher, as phi, phi or psi A R1 plus some lambda, which is a parameter, psi B R1 times psi A R2, but lambda here, plus psi B R2. Okay, this is neither that nor this. And they said, let me find out if I increase the distance between these two, how does this lambda and parameter, and do a variation calculation to find lambda, how does lambda change? Okay, so what they found was very interesting. So we are plotting lambda versus R for minimum expectation value with respect to lambda, right? Because the only parameter I have is lambda. Is that okay? Is the problem clear? And what they found is almost 1 and switches very fast to 0 at about R equals 1.6 R equilibrium. Is that okay? Now, so what it says is when lambda equals 1, you have a good MO theory. That means when you are at R less than 1.6, you have wave function which is a product of the LCAO wave function. On the other hand, when lambda becomes 0, right, you have a valence bond. So when the particles are going far apart, or the nuclear centers are going far apart, valence bond is good. When they are close by, molecular orbital. This is a switch. This is a switch from electrons which are moving around, which are delocalized. In MO, they are delocalized, to a system where they are localized. Is the idea clear? Now, why I'm interested in this is I would like to have functionals, this is for people who do DFT, check whether, we develop functionals, see whether they follow certain properties or not. Can I develop a correlation functional that reproduces this kind of behavior? As I go apart, it switches its behavior. It's like the problem in band gap problem also. So that's why I did this. And this you can now extend if I go to a multi-center thing. Right? If I go to a multi-center thing, the wave function in tight binding, I can write as summation e raised to I a dot r phi, which is a delocalized wave function. And if I stretch, do the electrons become localized in the system, which is basically a multi-center transition. Okay, so this is like a two-center metric. Okay, so this is something which I've been after, and then this should be a way of checking good functionals or develop functional. They'll do a good size consistency. This is known as the size consistency thing. That if you go far apart, the atoms remain neutral. Okay, so with this, I'll stop on this brief introduction to interaction and what it does. All right, all this metal insular transition. It does changes the nature of wave function as a function of size. It makes electrons go away, doesn't like two same spin electrons sit together, and that was also captured in something called the Hubbard model. Those of you who have studied this, right, where you put in the Hamiltonian, a Hopper term, and a term which costs energy if two electrons are at the same time. Okay? So that's this. Now with all this difficulty, and you can see, I gave you those 4 or 5 problems where we were doing, designing wave functions and things were behaving differently here and there. Can we have a unique here? That's number one. Number two, as I said, that if you have many, many particles, you cannot have that many mesh points. Can I have a theory that is like a fluid theory? Right? Just like when I do fluid dynamics, I cannot take care of each molecule motion. Just like that, instead I take up, density and current. So, in exactly the same manner, what we now have for many different formulations of density functions, right? Which is formulation of quantum mechanics of many electrons in terms of density. Well, this is for a steady state, right? And the time dependent counterpart would be in terms of rho r and j r current. And then I'll have this as time dependent. Okay? So that's the idea. You understand the connection with fluid. It's like fluid dynamics. Okay, and how we do it. So number one, I have to formulate it exactly. Number two, I have to then know that how to get quantities out of it. So first thing, if I want to do it in terms of density, I have to show that density indeed is a reasonable variable, that it satisfies certain properties, right? So first thing that we do is number one, show that rho r is as good a variable of many electron system as psi. Again, that's a huge demand, because now you notice this is rho r and psi is R1, R2, and all the way to n. Right? So this is Tn plus spin. And we are saying this is okay. How do we do that, right? So that's where the Hohenberg-Kohn theorem comes. And what it says, and I'm giving it without proof because the proof is very simple, there's some variation principle, that the ground state density rho r, right? You can map this exactly to the Hamiltonian system. Also, if I take rho r dr n, then I know that the kinetic energy operator is going to be minus 1/2, that is I square I equals 1 through n. I know VEE r, which is summation ij up to n 1 over ri minus rj. This is trivial. And third thing is that this rho should be able to give me the external. So what Hohenberg-Kohn theorem says is that there is a unique map from each given ground state density to the potential. It's determined unique. Okay? So I can write it like this. So 1-to-1 map. You cannot have two different potentials giving the same ground state. Is that okay? Now, so it establishes, right? This is establishes the equivalence of rho and the external, but does not give the description. So how to do it? We don't know. Alright? Now, to appreciate the beauty of this theorem, okay, let us see this. If I have a single particle, and I'm not talking about interaction particle. Oh, by the way, this is for, we should say, for a given interaction. That interaction is fixed. It could be Coulombic, it could be soft Coulombic, it could be whatever. Alright? Now to appreciate this, suppose I give you a single particle. Alright. Now I'm doing all this because this we are going to use later. Then I have phi r. Okay, single particle ground state object. And then you can write the external r as by inverting the Schrodinger equation 1/2 del square phi over phi plus some constant. That's perfectly fine, right? For example, if I have a harmonic oscillator, I know wave function is e raised to minus some alpha x squared. I do this and I get my answer. Right? So, single particle, that's fine. Even two particles, non-interacting, I can get it. Right? Try doing it for the density of three particles. To get the external rho. I'll pause here and wait for your comments. Can you do it? Given a density, so here this single particle case, this would have been this. Phi is root rho. What would we do in this case? And if I have 10 particles, can you do this? It is not interacting, not even interacting. And an equivalent problem would be, so I'm just making this potential. Two particles interacting.
So by varying the rho r until we not get the external minimum energy.
No, you vary rho r and what do you do?
To get the minimum the external.
No, I want to get the external potential from the density.
Minimum energy, we get the minimum energy.
You don't know the Hamiltonian. That's what I'm trying to get. Although I have given this statement that Hohenberg-Kohn theorem says that this happens, description is not there. In single particle case, or two particle interacting case, non-interacting case, it is there. I can do this. Okay? If I have more than two particles, if I have more than one orbital, I cannot do this. I just don't know how to do it. If I have two particles interacting, then also I don't know how to do it. So, description is not given. What you do know is it exists. Okay, so all we have said is that given a ground state density, I can in principle calculate the external, and therefore I can in principle calculate the wave function. It's just that I do not know how to do it. So now I have to develop the whole machinery to harness this. Okay, is the motivation clear? So how to harness this? And for that, given a ground state density, I know the Hamiltonian. Okay? I know the wave function therefore, and I can write therefore the wave function is given by the density at the symbolic value. Okay? And therefore, the energy, which is psi, is given by the ground state density. E I know is fixed, that operator is known. VEE is known, right? V external, either you can calculate from there or it's known. So I'll give you V external also. Psi rho is a functional of the density. That means from a rho, there is a map to the function to a number in real. So that map is known as a function. That's why density function. Alright? So now I know rho. If I given a rho, I can calculate energy, and this I'm going to keep V external. In V external. Although in principle you can get from rho to V external, I'll assume it's given. Okay? So it's a functional of rho. And then you can also show the variation principle for the energy. That means if for the corresponding V external I have the density rho, if I vary and calculate this, delta E, okay? This is 0 at corresponding wave. That's the variation principle. Variation of E up to first order is 0. And this is written as integration, something called the functional derivative, and all of you are familiar with it. This comes in Goldstein also when you do the action variation. Okay? Delta rho r dr. suppose, just for the heck of it, if you are given E rho equals, let me just write it. Suppose E rho is equal to some function of rho and grad of rho. We are, suppose, then the functional derivative delta E delta rho, this you done in the Lagrangian mechanics, is equal to grad of del f del grad rho. This is symbolic, this is all three components, minus del. Just to connect the action in Lagrangian mechanics is LDT, and you get delta E equals del L by del R V d by dt minus del L. Exactly the same thing. 2 has been replaced by rho. Grad of V, which is 2 by derivative with respect to time, has been replaced by derivative with respect to space. Yes?
So we are trying to find the
I
external.
cannot hear it.
We are trying to find the external given a row. So we should be doing the variation with the external. Why we are doing with row?
No. What is my basic variable? Rho. And what we have said is that keeping the V external the same, and I'll comment on that, I'm glad you asked this. If I change from 2 density to some delta rho, first order change is 0. Now I have to keep V external fixed, because remember when I do the variation principle, I cannot change the Hamiltonian. Hamiltonian is fixed. Is the wave function which is varying. When I am using the variational principle in terms of rho, I come to it through some wave function. I cannot be varying the Hamiltonian, otherwise I am changing the system. So what I should be writing, if you are so particular, V external is fixed. I keep that fixed. So I have some density, and I just, so for example, suppose I have a system, and there is some density. Suppose this is the exact density. Alright? And I know V external everything. Then I take the nearby density. Okay? With the same boundary condition. Then, if I calculate E for this density, subtract the true energy, right? First order variation is 0. Keeping V external fixed. That's the whole idea of variation. I hope I have answered the question. I cannot, when I am varying rho, I am just taking a particular rho and then varying around it. I cannot be adjusting the external accordingly. Then I am changing the problem. Anything else? Okay, so now this is what it is, that now that we have found that I can take the functional derivative and it should be 0, that's my argument. I should be varying E. So delta E should be 0, keeping V external fixed, and there is a condition. With the condition that integral rho r dr is equal to n, it remains fixed, and therefore integral delta rho r dr will remain 0. That's why I made this somewhere positive, somewhere negative, somewhere positive, somewhere negative. So that the integration is 0. Is that okay? Alright. So now with this condition, what you get is So delta E is delta E over delta rho dr, and I want this to be 0, and the condition is this, right? If this was completely arbitrary, this would have been 0. This is not completely arbitrary. So even if I have delta E, delta rho equals some constant mu, this is a CBC. This is also called the Lagrange multiplier technique. What you do is, you do d E minus mu integral rho r dr minus n, put a Lagrange multiplier here, and make it very easy. Both are the same thing. Either I can say, if I put a constraint, I can have it not 0, but a constant. Even then, the variation is 0. Okay? So that's the condition. This is the equation number 1. I still do not know what E rho is, but I have now proved a very powerful theorem that if I knew this, I can calculate the density directly. I still don't know how to map from that density to the Hamiltonian. I don't know how to map from that density to the wave function, but I am developing the machinery. I have the machinery, and we have to find out how to map this if I want to do anything meaningful, or how to express quantities of interest in terms of the density. If I can calculate the density and I can calculate the quantities of interest in terms of density rather than the wave function, my job is done. Right? Finally, I am interested in those observables. Right? So I found this equation, except that now, okay. Now remember, what is E? E is the expectation value of the current energy operator, which will also now be a functional of rho, plus VEE, which is also a functional of rho, plus the external potential, V external R rho R here. That's my E rho. Okay? And this I'm going to call F rho. What is F rho? F rho is a functional, is this expectation value, which is sine rho T plus VEE sine rho. You see, nowhere V external comes. I had rho, from rho I got some V external, from this I got psi, which is a function of rho, I can get rid of this, so this is a universal functional. In that, the picture of, it does not depend on which system I am talking about. It's universal. I found it exactly for one system, it's done. This is just like Newton's universal gravitation, right? It's the same for all planets. It doesn't depend on whether you're talking about the sun or the galaxies or whatever. Exactly in the same manner, if I can find it, this is universal, it applies to all the systems as a power. Is the idea clear? So, my equation becomes delta F rho, delta rho plus V external is equal to yes.
This is universal. V external same.
V external?
V external is same.
Yes.
So the value of
No, V external could be anything. It's a map. Given a row, right? F would be the same for lithium plus for helium and for a lithium solid, and for silicon semiconductor, if I can find it. It will not be difficult. does not depend on the external. Except that I don't know how to map it.
If it's functional of rho,
Yes.
density is different between these cases.
Yes, density could be different. So just like if I have a sine x, x could take different values. But sine is sine. In that sense. Right? The sine function does not change the behavior depending on the value. The value would be different. Right? Yes. Time up? 5 minutes, okay. So this is a universal function, and what I want to do now is define it in a slightly different way. And that's where all the math is going to come in. Okay? So, the other way of doing this now is, remember, I said that this mapping is for a given interaction. So suppose I produce the same row by a non-interacting. That is rho is the ground state of a non-interacting system. Then rho R to that V non-interacting will be unique. See, because if I give you a density, you don't know whether it is non-interacting or interacting. So if I can find a way of doing a calculation to non-interacting system, I'm fine. Alright? How do we do that? So this F rho, so I'll finish the Kohn-Sham and then we'll stop, is T rho plus VE rho, which I'm going to write as the classical interaction energy between electrons plus E, what is exchange correlation quantum mechanical, which is like that expectation value. But now I'm going to replace this by the non-interacting kinetic energy and add the difference, E minus ESA. And this I'm going to call EXCDFT. Alright? Once I do that, then what is my equation? By the way, ES rho, because it's non-interacting, is going to be in terms of some orbitals phi I minus r del square phi I, where phi I will also be functionals of rho. Okay? Then my equation is going to be delta TS delta rho plus the external is there plus the potential due to this. Again, by using that rule you can find out, and this is going to be V rho r prime over r minus r prime dr prime plus the functional derivative of this EXCDFT, which I'm going to call some VXC r, is equal to where VXC R is delta EXC DFT over delta rho R. These two are exactly the same equations because all these things are the same. Right? However, this is also true for non-interacting. Right? Now, non-interacting, the equivalent equation is, I'm going to erase this. Equivalent equation is minus 1/2 del square plus V external plus, let's call this V Hartree plus VXCR is equal to epsilon half phi I R. These two are equivalent. Remember earlier I was going from Schrodinger equation to this, now I'm going from here to there. And this gives me the density rho R to summation phi I R mod square. Here I was getting the density directly, now I'm getting it through this equation. Here, if I just look at this non-interacting system, the energy for non-interacting will be summation epsilon I, right? And I'm going to relate in the next lecture epsilon I max to mu. Just to keep you prepared, this mu is the same by construction, and this is the chemical potential, which is nothing but dE dN at the fixed V external. And in this system, dE dN is going to be when you remove, minimum dE dN is going to be when you remove particle from the uppermost orbital. So from here, mu is going to be epsilon. Nice. I'll stop here. I'll take any question about non-interacting particles. Now, if we go over to interacting electrons now. And I'll write the Hamiltonian ones in the list. Leave it there. Plus summation of ij prime, prime means I is not equal to j, 1 over Ri minus Rj. And first thing you notice is it's not a separable Hamiltonian anymore. Right? It's not a separable Hamiltonian, and therefore the wave function psi R1, R2, and so on can no longer be written as a product phi1, R1, phi2, R2, and so on. Right? You cannot write it as a product wave function. It's not a separable Hamiltonian anymore, and therefore you have to now do something more. Now, I just want you to recall that if we have a single particle equation, half del square plus some V external R, phi I R equals epsilon I, phi I R, we do know certain problems where we can solve this analytically, and I can also solve it numerically very easily. So let's say we take make a mesh to solve it of n points. Right, so I make a mesh of n points and then keep solving for whatever orbitals I'm doing n, right? Now suppose I want to solve this numerically. For n particles. Let's make this n points, mesh is n. Alright? Now, since I cannot separate, I'm in trouble. I'll need n raised to m. I cannot separate, right? Now imagine solving for 100 electrons, 10 electrons, and 100 mesh points. I've written it the other way. M for first, N for second, and so on. So M raised to n. Right? So then I get 10 raised to 20 points. Do you appreciate the number? It's a huge number, and I cannot just solve it. I mean, this kind of memory I don't have. So numerically, I just cannot, even for just 10 electrons, I cannot solve the problem. Right? So this is not possible. And that's what makes the problem very difficult. right? Now, counterpart would be classical, you do fluid mechanics and things like those where you take microscopic variables, right? You take the current, you take the density, and solve Navier-Stokes equation, Newton's law-based equation. We don't have it here right now, right? All we have is this, and this makes it next to impossible to solve, right? So this is out. Integrating the Schrodinger equation is out. You just cannot do it. Number one. Number two, no analytic solutions. Because even if you look at this equation, right, only very few potentials give you analytic solutions. Forget about it, you have 1 over r I minus rj. So mathematically, the terms you're going to have is psi, which will be not just r1, r2, and so on. You'll also have terms like r1 minus r2, r2 minus r3, and so on. And I just cannot imagine how to take that into account, right? So this is an impossible problem to solve. So we just give up and say, any many-body problem, many-vector problem, I just cannot solve neither analytically nor numerically, right? So memory required is too much. This I do not know. So what we have to do is now do some intelligent modeling, right? And so I'm just giving you background of this, how we go about doing this. So this is the heavy for doing this, right? And then see what happens. Now, some brute force methods would be. So first thing is the method of choice is variational principle for the energy. Are you familiar with variational principle? Anybody who is not? Okay, so what we do is, I can now design my functions like a choice of functions. One is brute force. I'll write psi, r1, r2, and so on as summation of some coefficient Cn times psi Slater determinant n. So I have a set of orbitals, right? And I make this Slater determinant expansion. I can go up to 10, 20, 30, whatever I like, whatever my capacity is. But this is a brute force method, and I determine this through variational principle. Just for the heck of it, let me just write. I take the expectation value with respect to psi and do d by d Cn equals 0. That's enough, right? That's one way of doing it. That will be absolutely brute force. And in fact, doing it this way, if you fix these orbitals, right, take only one configuration, that's known as Hartree-Fock theorem. One Slater determinant, all right? If you mix more, the multi-configuration Hartree-Fock. If you allow variation of this as well as the orbitals, that's configuration interaction theory, all right? The CI the other way, configuration interaction the other way. So anyway, this is one way. Other thing is, now we start thinking and work according to the problem. And that would be that I design a wave function. See here, you've just given all the freedom to the computer. Then you do this, you do this, you do this. Now we're saying, no, we'll design according to what I know about the system. In particular, if you have these terms, right, the Hamiltonian has these all terms, but it has in particular Ri minus Rj terms, right? And therefore, as I said earlier, the wave function would be something, and some terms which are Ri minus Rj. Now when I want to design the wave function, what I realized is that if there is an electron somewhere, right? Now yesterday we saw that if there are two parallel spin electrons, they avoid each other. Now in addition they have a repulsion, and repulsion is not only for this, repulsion is also for opposite spin. Even they avoid each other, right? So there should be a term. So suppose I'll just because I'm giving ideas, let's take two electrons. I keep going to these small systems because they make you visualize things, then you can do whatever you want to do. Now non-interacting, we said that the orbital is going to be phi, let's say first one, R1, phi 2, or phi 1 itself, R2. But now, let's say this is spin up, since they're both in the same space orbital, spin down, so there is no question of exchange. Exchange is only between parallel spins. Now what I want to do is, I want them to spend more time away, right, because they're repelling each other. So I may as well multiply by this by a function of R12, where R12 is mod R1